Okay, let me just reshare it. Right.
Okay.
Is it coming through now?
For me, yes.
Okay, good. All right, I'm just going to turn my camera off for this. Right, good afternoon, everyone. So to this session, we're going to have a look a little bit at HFSS in terms of the overview, but very specifically, we're going to have sort of a dive into antenna simulations and how we can do sort of large arrays and some of the tips and techniques that we have within HFSS to try and simplify the process, make it faster and easier for you guys to do these large simulations. So there we go. Right, so for those of you who are kind of new to us as QFinsoft, I'll give a little quick overview where we fit into the picture with Ansys. And then, as I said, we'll have a look at some different antenna array modeling strategies that we have within HFSS. And then I'll do a quick demonstration to show how we go about setting up these type of problems. So us as QFinsoft, we've been around for 25 years now. We are the leading, or we feel we're the leading computer-aided engineering software providers within Southern Africa. So our head office is in Pretoria, and we also have a branch down in the Western Cape in Stellenbosch, where myself and Lara are located. So our main business is servicing and supporting the Ansys suite of software. We do a lot of sales, pre-sales and support and training for the software, as well as we offer a lot of technical support behind the scenes in terms of consulting and other services for that. We're obviously located in South Africa, but we are servicing sort of particularly the Southern Africa, but also branching out into the rest of Africa as well. So expanding the reach as Africa is growing and developing. Then very quickly for Ansys, for those of you who are less familiar with that Ansys as a brand, Ansys is seen as the number one simulation software provider in the world. It is certainly the largest and offers a much bigger range of software options than a lot of other competitors. And that is because Ansys just focuses on simulation software. It doesn't sort of get distracted with other products. It's all about simulation and bringing value to customers through that means. Traditionally, when people think of simulation software, they always think of sort of the main physics. So your just FEA structures or CFD fluids or something like that. So not only has Ansys expanded this offering, but it's also about how we connect these different offerings together, bringing them into a system level model, combining different physics into a multi-physics approach, and then with also all the support services around it. So huge material libraries, cloud HPC solving capabilities for optimization, and so on. So they really try and offer the full range of products. And then also sort of in that, a lot of people feel that simulation really comes down to sort of the final design part or final phase of the design process, as kind of just some sort of verification check. But we feel from Ansys that we can really come in at every level, right from the concept design phase, trying to knock out all the bad designs quite early on so that we can save time and money and focus on the better designs. And then also there's a lot of products that have been coming in, particularly towards the end of the process, so manufacturing optimization, as well as maintenance and monitoring of products through their operational phases. So there's a large scope for where simulation can be used. And the product offering from Ansys has grown tremendously over the years, sort of bolstering their original offerings, but then also adding new physics and new capabilities across the board. So today we're just going to focus on the HFSS, so that's just one part of the electronics packages that we have. Right. So specifically looking now at HFSS, we talk about high frequency simulation tools. So HFSS focuses on the high frequency electromagnetic spectrum and all applications in that range. Okay, so typically RF microwave designs or areas, right down to also even PCBs and integrated circuit chips and that these days as well. Just because of the way the technology is growing and the capabilities and complexity is increasing day by day. And traditionally, Ansys is kind of seen as the gold, or HFSS, sorry, has been seen as the gold standard for high frequency simulation. And the reason for that is it's based on the FEA method, finite element analysis, has been its kind of core technology offering since the beginning. And obviously, we've added some extra solvers and techniques over the years to speed things up. But really, the FEA method is where we've kind of made our mark. And the whole reason for this is the FEA method is based on a meshed approach. So we take our geometry and then we create a mesh on it. And when we do this, we found that we're not actually solving the geometry anymore. We're solving the mesh because that's where the numbers are calculated. So it's all about how well that mesh represents our geometry or our product and physics that we're trying to capture. And to this end, we use what's called an adaptive meshing approach or automatic adaptive meshing. And what this does is the mesh will actually refine itself in areas of high gradients, high field gradients. And so that way we can get additional accuracy where we need it without adding any extra overhead. So we can focus our efforts around particular components and leave everything else fairly coarse. And then obviously we can capture large curvature and intricate shapes because of that. So that really gives us great flexibility for any type of product, but also great accuracy as well. So traditionally, we've always had the finite elements, but traditionally it really works well for smaller components or electrically smaller components, just because of the additional cost of computing resources that are needed. Obviously, hardware has come a long way and it's made things a lot easier. But over the years, we've also added additional technologies for larger systems where to try and save time, but still keep good accuracy. So this is when we bring in a tool called integral equations method. So this is very similar to a method of moments type approach, where we're looking at larger systems, flat open surfaces, and so on. So this, we can certainly look at larger designs through that. Sorry, wrong way. Then going to even larger systems, we incorporate SPR plus approach, which is a shooting bouncing array technique for very large scale systems. Okay, so we have these multiple techniques for different problems. And what's really nice about HFSS is that we can then also combine these methods together. So we use something called the domain decomposition method, which breaks up our solver domain into different regions, and then we can use different technologies or solving algorithms to solve the field in that area. So that way we can use the accuracy of the finite element method where it's needed, but then combine that with something like a SPR plus approach for large installed system models. Okay, and we'll use the domain decomposition method will be the basis of some of the techniques that we look at today. And through all this, it allows HFSS to really model any type of problem. We don't see HFSS as focusing in a particular area or type of analysis. It is very generic. It's physics-based, so we can really throw any shape or geometry at it. We set up the physics correctly, and we can model any type of problem. So we don't feel we're limited to a particular industry. So we go from anything from large-scale platform integration to an arrays down to small consumer products and installed performance there. and even biomedical applications. So we have some libraries for human body parts that we can then bring into HFSS and then see the effect of our components on the body. So we have quite versatile, and we feel that we're not limited to any particular application. And then another quite useful tool that we have at our disposal, which we also make use of today, is the idea of 3D components. Okay, so the idea is that there's kind of two ways to go about it. So the 3D component can be seen as a component that we've designed. It's never going to change, and it's something we're going to reuse again and again in other types of simulations. So it's kind of a building block of our particular problem. But also maybe it's a component that we want to share with one of our colleagues, or maybe with a supplier company, because they want to implement our, for example, our antenna and look at its install performance, but we don't actually want to give away our IP of what's actually going in there. So this example here, we're looking at this little blade antenna that we've got for this aircraft. We've done all the design and all the IP in there, but we need to share it with the aircraft manufacturer so that they can see if it's going to work on their platform. Obviously, we don't want to give away all the details of how this works, because maybe there's some proprietary information. So what we do is we share this as a 3D component. So essentially, it's just an exterior volume that represents the shape and size of our component, and also that the final fields that antenna has are saved with that, so we can share that information to the client, and they can put it into their model and use it as an active component without actually having to know what goes on inside there. So it's essentially a little black box that we can then share around, but it still has some meaning and usefulness to it. All right, so that's quite a nice technology. In fact, many manufacturers are offering the products they sell as 3D components. You can download them on the websites, and you can actually use them in your simulations. Okay, so this is also, again, some technology we will be working with today. Then just looking at the kind of techniques that we're going to work with for simulating arrays. So as we get to technologies increasing, our frequency ranges are needing to go up, and complexity of our systems are going up. We're finding more and more arrays are being used in different applications. Partly for the fact that they're small and modular, and they can then use that to sort of tweak their performance. But to do that, or to simulate that, we need to kind of say or understand at what level are we going to try and tackle this problem. Because if we have a very large array, maybe we can see this as a very simple approximation, that it's some sort of infinite array, that all the elements are behaving the same. The array is large enough that all the components are seeing the same field around them. So that's maybe one approach to have. The next is to say, well, okay, the array is large, but it's still only a finite size. And so we do need to account for all the edge effects that are happening at the elements towards the outer edge of our array. And then also the approaches we talk about today will also be appropriate for these frequency selective surfaces or metamaterials that are becoming very vogue at the moment, as a way to kind of understand their performance, because invariably they're also just repeating pieces of geometry in the design. All right, so with these different scales in mind, the different techniques we have is on the left there. We'll start at the very basic level with a unit cell. So this is where we take the infinite array sort of approximation, where we assume all the elements are the same and they get all affected equally. Okay, so in this case, we only need to consider one active element within the array, and that allows for obviously a very quick, efficient simulation. So this is usually a good starting place when we design an array, just to get a kind of a feel for how these elements perform before we start throwing them together into a bigger system. Then the next level is the finite array domain decomposition method. So this is where we take our unit cell and we replicate this into some sort of array pattern. And what this does is, it's very efficient in the sense that we're working with the same unit array. So it's the same geometry and the same mesh that just gets replicated. And then all the solver does is just really account for its position in the array and how that affects its signal. So obviously the elements on the outer edge of the array will see a very different pattern to the elements on the inside of that array. Okay, so it's a very quick, efficient method compared to the next option, which is the explicit array. So this is where we explicitly model the entire design. All the elements are there, they're all active, and we account for everything that goes on there. So this is obviously the most accurate because we're including everything and we're solving it all together in one go. But it's also going to be the most time-consuming and heavy on resources. So we try and stay away from it as far as we can, but obviously it depends on the application. So when with these methods in mind, we always need to try and decide what is our goal here, and what do we have, hardware resources do we have available to us, and that might govern where we go for the very simple unit array, which is very fast and cheap, or do we need to go to a more rigorous type model? Okay. And if we just have a look at, obviously the goal of today is to look at the some of the faster, easier methods to solve these problems. So if we look at some of the statistics here, just modeling a 10 by 10 micropatch array, we can see here that if we compare the explicit model, which is this image on the right here, to our finite array domain decomposition method, we can see that there is a dramatic drop in simulation time, 24 minutes versus almost 4 hours. And we're also using a fraction of the RAM, okay? Because remember, we only using a single, or we've got the same repeating piece of geometry and mesh, and we're just basically correcting for the field properties throughout the footprint there. So a dramatic speed up in RAM and solution time. And you can see here at the bottom, if we look at our sort of beam pattern here, that it's a very similar pattern. It's hard to distinguish the difference between the two. So we're going to get a massive saving with very little loss in accuracy. Okay, so the way we go about building these finite arrays, so we take our unit cell and we build it into array. We use this array matrix here to this array mask to define the pattern of the array. So using our little unit cell, we can customize the shape that our larger array is going to take, and it really cuts down on the amount of effort that we need. So, we can choose between active elements. We can include our geometry, but just switch them off so they become passive. So that's, maybe helping to form the beam around the outer edges of the array. And we can also choose for padding elements. So just blank cells that actually have zero components there. They're just open space, because maybe we need that to sort of, again, to form the beam around the edges of the antenna. So just with a few clicks, we can essentially create quite complex arrangements. So we can do sort of fairly standard, regular sparse arrays here, or we can even get some quite fancy shaped arrays. So it's really just taking this grid, populating it with our different antenna elements that our unit cells that we've created. Okay, and then the idea is that we're not, obviously a lot of the picture shows sort of a square rectangular shapes, but we're not limited to that. It all comes down to the shape of the actual unit cell that we use as the foundation for our model. So we can use hexagonal shapes. We can use also rectangular, but sort of offset. You can see we've only using partial overlap of our opposing faces there, so we can get some sort of triangular lattice structure from that. So we can really, as long as basically what we're aiming for here is that our faces of our unit cells do need to match up with essentially what their neighbor would be. So as long as we have that kind of pattern, we can get quite creative with these shapes. Then taking this a step further now, so moving to much more complex shapes where we still have an array, but maybe parts of the array are not necessarily the same element. We can't just assume it's a unit cell everywhere. That's where we bring in this technology of the 3D component. So we can then use essentially building blocks for our array. And we can then construct our array from a lot of repeating pieces here. So for example, this array, we've got an active element, internal element there with some sort of cover over it, a radome cover. But then also we can have corner pieces for our radome cover. We can have covered areas, but where there's no active element, and we can have edge pieces as well. And you can see that these elements get repeated all the way throughout our larger design. And so again, we can very quickly replicate our design from these small, few building blocks. So for example, we've taken our array mask here, and we can populate that mask with all of our individual elements in the right places to get build the array that we want. And we can even now, in the latest release, we can use a CSV file to define this array mask. So as things get bigger and there's more components to work with, and we're shifting rotations as well as looking at our sort of phase and magnitude there for our beam steering, we can define all that externally in a CSV file and just import that. All right, and basically how this works is using the Mesh Fusion technology, which is a fairly new process where we can mesh each of these building blocks into separately as their own unique entities, and we can then replicate those little pieces of mesh throughout the body. Okay, so the idea is that we don't need to have a conformal mesh on these bodies. We can use the individual mesh settings that are appropriate for each building block, and then we can then stitch these together into the global model. Okay, so again, we're not limited by meshing. We can actually use the best mesh technology and boundary conditions and whatever for each individual element, so we can therefore end up with the best picture overall. And for example, here we look at this could be some sort of device under test process where we've got our main antenna. This can be modeled with its or meshed with its own technology, so more typical 3D FEA mesh there. And then we might even have a flat planar components. In this case, we've got a touch screen with details down to 300 microns that requires a very completely different mesh approach to this antenna. And then obviously we got the larger chamber as well that we then need to account for. So we can throw all these different mesh technologies together and just use the most appropriate settings for the different components. And that way we can achieve really good accuracy, but still try and get a balance of efficiency as well. Okay, and then just some last little stats on that. So in this example, so the little graph on that is different to this antenna mask here, but it's just saying that we can take this 3D component array. In this case, we've created a 6x6 dual Vivaldi array. And if we look at using that finite array decomposition method, where it's essentially just the single unit cell that gets repeated, and then we compare that to this 3D component approach, we get a significant drop in memory. We're using even less than half of that, and our runtime drops from 35 minutes to about 6 minutes. So that's a massive drop in time saving and resources for what can be quite a complex type array that we can construct from that. All right, so then I'm going to switch over now into demonstration mode, or I'm just going to actually run through the setup of some of these different array types and show you how we can then go and create these different methods. Yeah, while I'm switching over, are there any questions from the audience? Okay, no questions. Can everyone still see my screen okay?
Yeah, Evan, we can still see your screen. I don't think there's any questions now.
Okay, so what we're starting off here, this is a little patch antenna that we have. So we just have a little block of substrate there in green with our little copper trace on top there. What we are doing to drive this, we have a little port in the back there. So it's just a simple little rectangular surface that is a lump port that is driving this little antenna there. And then we also have a radome surface up top here. So this will just be some sort of, this is a Teflon component, just representing what would normally be a cover for this antenna. And so we're going to just have a look at modeling this as a little unit cell. So now that we've got our basic geometry, we need to create a region around this, because with the FEA method, we always need to mesh a volume, and that's where the field values get solved. So here we can create a region around our model. So if we use this region, it's an automatic region that will automatically wrap around all the geometry components that we are using. And that allows us to, as we change and manipulate the size of our model, it will automatically change to be the value that, or the size that we need. Okay, then what I'm going to do is, obviously around the edges, we want it all to be touching our model, but then I'm just going to add I'm just using a parameter there, a variable, to govern that value. Let me just check if I've got it. That's radv with a capital. So we can then go ahead and create our box around here, but let me just, if I go edit this now. So using my variable that I've calculated, it will automatically pick that up and assign that as a length. So why is it not picking up radv? These things always happen in a demo. Why is it not picking up that value now? Sorry about this, guys. There's always something that happens.
You'll get it sorted soon, don't worry. It's typical what happens in demos.
Yeah. So you can see I've just added a 50% padding on these. Oh, sorry. That's why I think it's actually be an absolute offset. That makes a little bit more sense, because that's a very small percentage there. Trying to do two things at once here. Okay, so we now created our region. It's now snapping to the edges of our geometry, and we've given it a little bit of space above and below our components there for the field to propagate out. For now, we're just going to leave it as the default vacuum material, but we can assign that to whatever material we want. Okay, then we also need to define the boundaries for our model. So what is actually constraining at the edges of, or how does the field behave at the edges of our domain? At the moment, the only boundary we have is this a finite conductivity boundary on the copper elements of our substrate here, of our active components. But now we need to obviously put some boundaries on the outer edge of our model. So if we select the region, and then we can go assign boundaries, we want to assign essentially these lattice pair boundaries, which are going to tell the solver how to connect these different unit cells together. Because obviously we need to have repeating geometry, and so we need to connect these outer surfaces together. We can either do that manually through creating matching primary and secondary boundaries, or because we're going to create, we know our end goal is to create an array pattern from this. We can use this auto-identify lattice pair. We give it the basic or the main dimensions that we're working with our component here. So in our X and Y domain directions, that's where we're going to pattern this unit cell. So if we set that up, then you can see it's automatically created these lattice pair boundaries. And these are essentially just matching primary, secondary boundaries at opposite faces. Okay, so when we pattern this out, it'll use those boundaries as reference. Then we just need to do some the top and bottom boundaries. So I'm just going to select face at the bottom here, and I'm going to assign that as just simply a radiation boundary, which will be fine for the purposes of this demo. And at the top face as well, I will go and assign a radiation boundary as well. Okay, so now we've defined the boundaries at the extent of our model. You can see this is our lump port excitation there that is going to be driving the signal in the model. So what we can do with these unit cells is, for example, this top face, we can also assign a flowk port. So in this case, sorry, this will be actually as excitation there. So we can define a flowk port to drive the signal into our array, particularly if it's going to be some sort of metamaterial, selective surface type material. But for in this case, we're happy to just drive our array with the lump port there. Also, and as we get the flowk port's also only really valid for these unit cells. When we start getting to the big array patterns, we do need to revert to something like either a radiation boundary or a wave port or some more standard type of port arrangement. Okay. Then for our analysis, we can add a solution setup. And for this one, we'll choose an advanced setup. Here we're going to define our main frequency. So this is the design frequency of the system. It's going to be 77 gigahertz. And what this does is allows the automatic adaptive meshing will focus around that frequency. So it uses the wavelength of that frequency to govern the mesh size, and so it will adapt the mesh or give the mesh the best accuracy around that particular frequency. Then we also will define how many passes that we do for our adaptive model or adaptive meshing approach. And so that will set that to 10. Okay. In this case here, we're just going to be running with the direct solver because that's going to be our fastest method. You'll see later on we'll switch over to the domain decomposition model for the larger arrays. Okay, so we define that as okay, and then immediately it asks us for a frequency sweep. Obviously, if we're just solving for a single frequency, we don't need this, but if we wanted to do a larger range to see how well this component performs, then we can define a range here. Okay. I think that's fine for now. So in this case here, if we have a look, if we go to simulation, we go to validate, we can see that we've correctly applied all the information that the solver needs to progress. So now we can go ahead and solve. But just for time's sake, I've already solved the model beforehand, just so that we can go ahead and look at the results there. Okay, so a couple of the options that we can create are for example, I've done an S-parameter plot here just to see how well we actually match our targets here. So our target being at 77. So in this case, I can create a marker. I want an X marker. I can set that to be 77. Okay, so I can use this marker at, or just for this case, at my target frequency and see, well, how well am I replicating it there. In this case, we can see that we're not really quite on board there. So obviously, we need our sort of theoretical assumptions don't quite work so well for the actual component. And so maybe we need to go and do some fine tuning of our component to get it to that frequency. But that's not quite the scope of where we are today. I just wanted to show this graph here because the blue sweep has come, well, there's two curves here. The blue one is from this unit cell that we've solved with a radiation boundary. And the orange one is the same unit cell, but where we've used a flowcate port to solve it. So just to kind of make you aware that sometimes there are slight deviations there with the different boundaries. If we are going to work with an infinite array approach, this flowcate port does work quite well, or does gives us an extra little bit of flexibility there. Okay, but then well, let's start with this one. So for 2D, you can see we can get our gain plots. So this is where we've created a gain or slice through of our elevation to have a look at our beam profile. And again, just in blue, they're comparing with a idealized flowcate port assumption. Okay, so that's fairly straightforward for our unit cells. Then what we can do then, once we've got our unit cell, is we can, if we're happy with its performance and we want to now go and have a look at a finite array version of this, we select all of our geometry, and then we can go to create 3D components. So this will just help us down the line to actually go ahead and reuse these individual elements in our system. So we can define all information with this 3D component that will go with it. We can assign all the different, which bodies we want to actually include and what materials they are, what boundaries and excitations were used. So you can see our lump port is going to be going with this. Also, if we have any parameters that govern the size of our model, these can be shipped with it. So if we want to change the size of this little component later on, we can do that as well in our array model. Okay. So yeah, if we're happy with that, then you can just go ahead and save it as a 3D component. When we're in our finite array method here, so this is where we've added our 3D components. So we've just gone for browse 3D component to find the model that we need. So that's been imported here. And so you can see all the geometry has come with it that we've defined previously, as well as our excitation as well. So this is the little lump port there that's driving the model. Okay. But now what we need to do is go and set up our finite array. And so this is where we're going to use the finite array decomposition method because it's the same repeating geometry. So we go to model and create array. And you can see here, because we've set up these lattice pair boundaries from our unit cell, it's picking them up and it's using them as a reference for the direction in which we're going to propagate this antenna pattern. So in this case, we're going to go for a 5x5 array, and we can also choose to add some padding cells around that. So the actual active elements will be a 5 by 5, and then there'll be an additional region around that where it's just empty space. And so that will be handled automatically for us. Let's set this to visible because we want to see what it looks like. And you can see here that we have our little 3D component here. So this is our little unit cell that we're going to have. And now we can populate our array mask here. So we can, in this case, just drag and click and drag because we just got a single element, and all of them are going to be considered active. Okay, if we want to maybe turn one or two of them off, we can do that by selecting passive and go and choosing the particular ones we want to be passive. So we can play around with different combinations there. Okay, so then we go to apply. And you can see now we have our array, our 5 by 5, and all the elements are sort of numbered accordingly to their pattern. Okay. So essentially we are working with this main entity here, but these are just shown for sort of visualization purposes. All right. The rest of the setup is the same. So we take our single frequency there, 77 gigahertz. We'll also do just 10 passes and so on to solve our model. So it is literally as simple as that to set up our new model. Okay, then I'm going to switch over again to our solved model just to save a bit of time. So this particular array takes about 40 minutes to do this frequency sweep. So sweeping from 50 to 105 gigahertz takes about 40 minutes on 4 cores. So it's relatively efficient. Obviously, if we're just solving for a single frequency point, say at 77 gigahertz, then obviously it goes much quicker. All right. So if we have a look at our results, obviously here there's a little blip there because I didn't finish solving the whole thing. But we can still see that we can pick up our parameter plots there. In this case, what we can do is also create a field pattern. So first, what we need to do to create our field pattern is we need to create our sort of radiation surfaces, as we call it. Okay, so let me actually just show. So we go here, insert far field setup, and create an infinite sphere. And this is where we define the range of angles over which we're going to calculate our radiated pattern. Okay, so in this case, we're taking the far field approach, and we can then choose if we just want to do a full 360 sphere or just a quarter or some other part of it. It's usually not too, doesn't take too much to calculate this, so you can usually do the full one, but sometimes for particularly, if you're just doing an elevation plot or a azimuth plot or something, then you want to limit these to a particular plane. All right. So, for example, now we want to have a look at our full field sort of shape, beam pattern. So we can create our far field approach or far field report. We go to 3D polar plot. In this case, we're selecting our 3D value there. We want to plot with using directivity as our variable, and we'll scale it by dB there. So we can create a new report, and you can see that we have our resulting beam pattern there. Okay, so we can have a look and see if it makes sense to us. What we can then also do is plot this on our actual geometry as well. So we can go right-click on there and go Show in Modeler window. So if we go back to our main window, we can see there's our radiated pattern. Obviously, it doesn't look very big. So let's go down here to Plot Fields, Radiation Field, and you can see that. Okay, I think this is the second one is the one I've sent here. So we can then choose, pick and choose which plots we want to show on our 3D model. So we've got our transparency there and our scale. So I think let's scale this up a few times and see if that makes better. So now we can see how our antenna pattern changes with our, or how it relates to our geometry. Okay, so obviously we can see that this is our full antenna pattern for this array that we've created. If, for example, we want to go and say, well, what happens if we change our sources? You can see in this case here, so I went to excitations and edit sources. And in this case, all the active antenna elements are firing at the same time. So we can go ahead and change this if we want to. For example, I'm just going to switch them all off, essentially. Just a couple. Okay, and if we go to apply, then you can see here that now our radiated pattern changes back to what is essentially just this 1-by-1 unit cell pattern that's going to be a little bit sort of altered because it's now got all these surrounding components, and these components are all passive. So this is essentially we can switch between different excitation states just by changing our source patterns, and we can see how these different elements are actually excited. And yeah, let me just change this all back. So you can see, well, we don't actually have to resolve our entire array again. This is in effect a post-processing operation to then go and just access all this information. All right. So also what we can see here, just actually remove that. So here we can see our beam pattern for our antenna array. So this is now with all the elements excited. You can see that they're for two different azimuth directions there, the 0 and 90 degrees. So you can see all our lobes there. And just what can be quite nice to compare as well. For example, if we go to our last gain, so we can copy data from a different project, bring that down here into our model, and then we can paste that there. So now we can see how our radiated pattern from a previous design and how that compares to this current model. So we can see that for this 5x5 array, we are getting better directivity there, but you know, and we can see where all the other side lobes and everything are created. Okay, so that is our finite array method. And just lastly, to show you here for the multi-cell approach. So this is just a sort of a slight evolution of that, of what we've seen now already. So in this case here, we've got a slightly more complex array. It's the same patch antenna with radome, but now we're going to include the sides of our array. Okay, so we've got additional elements here that make up the geometry around the side of our array. So we can take into account these edge effects. So you can see here that we've got all these different bodies, and they all come in with their own materials and shapes and everything. Okay, so they've been imported here under 3D components. Then we do the same as before. We go to model, we go create array, and in this case, we just want I think just a 2x2 matrix that we're going to do. Sorry, we need to do 8 because we need to include all the other components. In this case, we're not going to do padding because we essentially have a padding cell as part of our 3D components. And you can see here now that we have a whole list of different components that we can drag into our antenna mask. Okay, so we can then essentially just start populating this model. Just trying to remember all the different pieces here. Let me just check my notes. Yeah. So yeah, before I go too much further, so when we put these elements in, we also need to give it an orientation, because you can see here in the geometry, some of these components are, the edge pieces, but we obviously need to make sure that they face in the correct manner. So when we input our components into this array mask, we do need to give it its rotation angle as well. Okay, so I'm just defining the shape there for that. And then the same for all these other components as well. So these are now the corner elements. Go in there. Yeah, these guys are just the same because they're just, okay, well, so I'm just basically clicking and dragging my mouse and it automatically populates these cells. And then we'll go do that. All right, so let's apply, and hopefully you've got all the directions and everything correct. So you can see here that if I look in my model, kind of see through all the different sort of lines there, blocks, you can see that the basic shape of my antenna array of this radome has been created. And if we zoom in on the top, you can see here that I've got my 4 active elements in there with the cover that surrounds them. Okay. And then essentially everything else is the same. So even just also to note, in this case, because of our 3D components, we've only got one 3D component that we're copying. So we only see the one excitation, because obviously this excitation gets copied for all the active antenna elements. It is only through this edit sources option that we can then activate the different elements. Okay, if we then go ahead to our results, for example, we can now see our antenna array. So I think in this case here, also again, I just have the single, see, we've just got our single active element there that is actually driving this field at the moment. So let's go activate all of them. Takes a while just to update all the components that I've defined, all the post-processing elements. Okay, and there we go. Now we have our full array pattern for the actual fully active array, and you can see that our sort of final radiated pattern looks a little bit more realistic there. We can go and show in the modeler window. You can see actually here we've got multiple elements. Let's just hide that for now. Smaller. Okay. So we can see here that this is our radiated pattern relative to our antenna array. Let's actually just transparency. Yeah, it's a little bit better there. So you can still kind of see the array on the inside. Okay, and just some other components or just things for those who are not so as familiar with HFSS, there's a couple of other options that we can then also view as well. So we're not just limited to radiated fields. For example, we can also then plot our domains as well. There we go. So for example, here I've created an E-field plot for our just top surface of our substrate. So this was fairly simple. We can go select our surface there. Sorry, substrate there. We go to field overlays, plot E-field. In this case, I want to plot the complex component of that. So I can just select that. and then we get our E field on that surface. So we can see here that our E field is concentrated around the edges of those patches. So let's go, if we go hide this, ability. Not like that, okay. Okay, so now on that same substrate or top surface of the substrate where I plotted my E field, I've now plotted my mesh. So this is the FEA mesh that gets used for our solution. So you can see here how the mesh has adaptively refined to the edges of those little patches, because that's where the field is going to be the most intense. So we get our accuracy by having the mesh adapt there and to refine and resolve or give a better resolution of that field values there. And you can also see how all these different building blocks of this array have a different mesh. So this is this mesh fusion technique that we've used, where each element gets meshed independently, and then everything gets stitched together into the final complete model. All right, and I think we're kind of running out of time there, so I will wrap it up. Just one more thing to note for those of you who want to do calculate beam steering. If you go here, you can right-click on the design. You go to Toolkit and go finite array beam angle. Let me just bring it across here. And so here we can then define our theta and phi angles to steer the beam, and it will calculate the phase delay between all the different sources that we have in our model. So again, if we just quickly shift to the final model, we've done that here. So if we go to edit sources, you'll see now that instead of just scaling as a 1, we now have a scaling factor there, as well as a phase delay for the different units, and that will create a steered angle beam for us. Okay, so if we go have a look in the results here, for example, we can see how steering the angle from 0 down to 30 degrees, how that changes the beam shape. All right, so again, fairly simple, just like changing the excitations. We can then steer the beam. Obviously, every time you change the beam steer angle, you do need to resolve the whole model. That is, it's not just a quick post-processing thing, so you do have to change or resolve the model, but it is as simple as changing a few numbers in that little toolkit. All right, thank you. I think I'll leave it there. I won't take up more of your time. If there's any more questions, we can always take this further and show other tips and tricks around arrays.
Thanks a lot, Evan. I think there is a question in the chat for you.
Yeah, let's have a look here.
Could you throw some light on how to apply antenna array mask using CSV file? As mentioned at some point during the presentation.
Yeah. Okay. So to use a CSV file, let's just go back to this one here. Okay, all these are locked out. I need to save everything. Make a copy of this. Okay, so we have the option to, when we create our array, we could obviously create it using that square template that we've seen already, or we can create this through a CSV file. So just selecting a CSV and importing it. And essentially what it does is it just has already the distribution of where the components are and what order they're placed, what rotation they are, as well as what their phases are, phase shifts and source power. So if you are steering the beam, for example. So what we can do is we can export our existing array to a CSV file. So let's just go there. Okay, so if we do have an existing array, we do have the option to create an existing one. Then when we go bring in the CSV file and this other blank model, I can select that file, and you can see that it immediately creates that. Let me just go actually open the file. Save it now. Oh, okay, wrong folder. All right, so this is the CSV file that was generated. Fairly simple for this particular array. So in this case, we obviously only had one component that was brought in. So here we define our 5x5 vector array. So obviously these arrays will be picked up based on this lattice pair boundaries that we defined, and that comes from your 3D component. So this particular 3D component, let's go have a look at here. Okay, so remember when we defined our initial component, we have these lattice pairs. So these are the opposing surfaces that get repeated. Okay, so essentially this block, this surface on the top left there, that will be touching the bottom right when we pattern our model. Okay, and that arrow gives us the direction in which the pattern is going to occur. So from those lattice pairs, that defines our X, Y, essentially our AB vectors for the shape of our array. We only have a single component in there with a single excitation. And in this case here, this is where we start actually looking at the sources. Okay, so we can see that if we do need to, so the source is up here because we just have a single source. So in this case, we're just powering it with 1 watt and 0 degrees. But then in the array, we can then alter all of these. For example, if we do some beam steering, we'll see it will look a lot different. So actually, let's go back here to beam steering. So this one will give us a little bit more. So let me just save it in somewhere a little bit more useful. Okay. So here is a slightly more complex one, in the sense that we have more components, and also we defining our phase shift here. Okay, so you can see here we have now multiple components in our list. We have 4 sources because we have 4 different elements in this pattern, and you can see they've all had some sort of phase shift between them. And then this array down here is where we've got this list here is where we've got all the positioning of all the different components, as well as their rotational angles, if we had to rotate them. Okay, so yeah, once you've got your basic array, you can export it to get this template, and then you can modify this template for future reference. Well, does that answer your question?
Thanks, Evan. Yes, they're saying, Savara is saying yes, thanks. It's answering the question.
Okay, great. Yeah, and if there's anything else you guys think of after the session, please reach out to us. And you can email us at support@qfunsoft.co.za, and ask any questions, and we'll get back to you on that. Apologies again for running over time, but this session has been recorded and we will